So, Web3 basics. Super excited for this presentation. So, some of my ideas behind this presentation is I wanted to be able to, whether you're coming into Web3, never have been a user before, you've never done any Web3 development before, or you're somebody who's done one of those two things. Either you used a Web3 app or you've developed some things on Web3. I wanted you to be able to take away something from these slides. So hopefully all of you fit those criteria and you find that these are very helpful in some way or another. So we'll go ahead and dive in with that in mind. So first I want to think about the big picture because I kind of want to zoom out and take a look at what we're looking at from a high level before we dive into a little bit behind the scenes, the nitty gritty that's going to help us understand Web3 a little bit closer. Okay, so here you can see I've kind of divided this slide up into two things. There's vertically, so if you look on top, they're sending a transaction and blockchain state, and on the bottom, they're sending a transaction and blockchain state. What I want to do is I want to make the bottom picture here. Now, I know not everybody who's going to be watching this video or who is here today is a Web3 developer, or ever going to be a Web3 developer, but I want to make what's going on the bottom half a little bit easier to understand, even if you never get into the code yourselves. Meanwhile, up above on the top half here, we have what a knowledgeable Web3 user might understand is happening behind the scenes for a blockchain. So if you've been using a Web3 app in the last few years, you may have used a Web3 wallet, most likely MetaMask, to sign a transaction and send that transaction to an EVM node. And those EVM nodes all communicate to come up with a consensus, some state that they agree upon. And the things that we care about as a Web3 user is the EVM blockchain state that you see in the top right, which is your account. If you have an account, you know that your Ether is stored there. If you're on Polygon or another EVM compatible chain, it might be Matic or some other native currency. You might have ERC20 tokens on that chain. These are going to be as opposed to NFTs, which are also tokens. That's what the T in NFT stands for. ERC20 tokens are exchangeable one for one. NFTs stands for non-fungible tokens. They are not exchangeable one for one, meaning they have unique characteristics that make them have their own identity or their own ID that are not going to be necessarily interchangeable one for the other. So these are going to be the differences between the two, but we can categorize them both as tokens. They're a blockchain state that we care about. And then also we have protocols. We have things that we interact with, programs and websites that we interact with to be able to, trade these tokens or to be able to do something on the blockchain that is going to be important to us. Okay, so we're going to get a little bit closer to what's happening down below as we go through these slides. And I'm going to come back to this image so that we can understand this a little bit better. So one thing before we jump in here is I do want to mention that there are some constraints to smart contracts. So you may have heard this term, which is a bit nerdy, but you may have heard this term, smart contracts are Turing complete. If you don't know what that means, that's fine. It basically just means they can do anything you could imagine that a program can do. So there are no constraints to what you can put into a smart contract, or at least what you could code into a smart contract. There's nothing that they can't do that a program could otherwise do. However, that doesn't mean that there aren't constraints. You may be wondering, why haven't we seen something like a decentralized rideshare, like a Lyft or an Uber? Why aren't these web applications out there? Since I came into this space many years ago, I know people have been talking about these ideas, like, what would a decentralized Uber, decentralized Lyft look like? Well, there's a reason why these things haven't really shown up just yet, because there are actually constraints within the environment that smart contracts are executed. These constraints include all transactions incur a cost. This is going to be a big constraint that makes a lot of Web3 applications things that aren't necessarily as easy to develop in the Web2 world, right? In a Web2 world, you could have a forum where the forum is living on a server and a user can make a post and that's going to be free to them, right? It's just going to save some data to a database and it doesn't necessarily cost a significant amount to save that data to a database. But in a blockchain, every transaction incurs a cost. So while you're going to have those transactions and the state that's going to change via those transactions always exists forever, there's a cost that's associated to that that makes it difficult to create these web applications, because you need to have the user pay for those costs, or you can abstract that away, but somebody at the end of the day has to pay for that cost of a transaction. There's also a limit on the amount of execution that can occur within a transaction and within a block. We'll talk about what a block is, but there's a limit on the execution that you can have. And this is because all the execution is going to occur on all these machines, right? So if you have a blockchain network, you are expecting that your transaction is going to occur on all the machines that are supporting that network. That means that storing any data on the blockchain costs significantly, because you're asking all those blockchain machines to store that data not only now, but until the end of time if they're going to store the entire blockchain state. So by making a change to the blockchain state, whether it's interacting with Uniswap or it's adding an ERC20 token or any of the state changes that we talked about, any of the state that we talked about, you are asking that to be stored forever. Unless there are some changes to the blockchain that allow us to sort of get away with some trade-offs with maybe not storing the data forever, but I'll leave that out of the picture. Some of this is going to be simplifications for the purposes of the presentation, but you can imagine having to store that data for at least a significant period of time. And there's a lot more developer pain points where that comes from, interacting with blockchains at scale. I'm going to be talking about a lot of these developer pain points, and I'm especially going to be talking about how Alchemy solves these developer pain points as we go through these slides. So let's take a look at some of that. So now we're going to be going behind the scenes. We're going to go behind the curtain, take a look at what's actually happening in that big picture, but from maybe more of a Web3 developer standpoint. So let's go ahead and jump in. So everything begins at an externally owned account. So I want you to kind of score your own EOA knowledge. Maybe you've never seen this acronym before, in which case I want to tell you that EOA stands for externally owned account. Despite that it sounds kind of scary, you could just imagine this means that you have somebody has a private key and a public key. We'll talk about what these are in a moment as well. And that private key, public key is what allows them to interact with the blockchain, allows them to sign a transaction and send it to a blockchain node. So every EOA has a private key and public key pair. So if you know that, give yourself 2 points. If you knew the acronym and private key, public key pair. Every transaction begins at an EOA. So if you want a transaction to occur on the blockchain, it has to start at an EOA. Smart contracts cannot start transactions on the blockchain. That means that even if we abstract away transactions using account abstraction, at the end of the day, an EOA, a private public key pair, is signing that transaction at the end of the day. Don't worry if this is sounding a little too technical. We'll go into it a little bit closer. EOAs sign transactions using EXTA. If you know that and you knew the other 3 things, give yourself a 4 out of 4, and we'll hopefully there's still a lot that you can take away from these slides on EOA. So we're going to talk about, before we go into EOAs a little bit more closely, I'm going to talk about digital signatures. So digital signatures, this is a bit of a tangent, but it's going to help us understand how transactions are authenticated in the network. So what I want to do is I want to talk about something called symmetric key cryptography. And that may sound like a bit of a mouthful. It may sound a little bit scary, but it's not that scary at the end of the day. Symmetric key cryptography just means that there's a communication that occurs, and on both sides of that communication, the same key is used to encrypt and decrypt the message. So there's a really good example here that we could use, which is if we have a communication across an unsecured channel, we might have the same key on both sides. For these examples here, I have this message, hello world. So you can imagine that Bob and Alice are trying to communicate, and Bob wants to send hello world over to Alice. Bob might shift the message, each character in the message, so the H, the E, the L, the L, the O, he might shift it over by 1, which is going to give him IFMMP, XPSME. And then on the other side, Alice is going to back by 1, which is going to give them, oops, sorry, there's someone.
This meeting, the Hack 101, so like super technical.
Javon, your mic's on.
Javon, you're there you go.
Thanks, Al. Cool. So you could shift over all of these characters here by 1, which Alice and Bob have agreed ahead of time that this is the key. We're going to shift it over by 1. They could have chose to shift it over by 2, by 3, by 4, by 5, but they chose 1 in this particular case. Now, that's not the greatest security ever incorporated into a symmetric key cryptography. A better key would be a key that's like the size of the message. So the second example there with a key 324, where you're shifting over the first character by 3, the second character by 2, and the third character by 4 is going to be a much better example of a key. The reason is like somebody could take a look at the first example and they could see that there's M is repeated 3 times in that encrypted thing, and they could know that M is a character that is most likely to be used a lot in the English language, and they might be able to deduce what that letter is in the first example, and then maybe they might be able to crack our key. The second example is much more secure. The bigger the key is, the better in that case, right? So the idea here is that symmetric key cryptography is they have the same key on both ends. For the first example, it's 1. For the second example, it's 324, and they know to shift these characters over by that key. You could also do other translations, not just shifting the characters over, but this is just a very easy example of a symmetric key cryptography, where Bob and Alice want to communicate, and they have the same key on both ends of the communication. So this brings us to asymmetric key cryptography, which is really where I wanted to get to. This is also called public key cryptography. Now, if you understood symmetric key cryptography is having the same key on both ends of the communication, then it may be easy to understand that asymmetric key is having a different key on both ends of the communication, right? So in this case, we're going to be talking about public key cryptography. Public key is a revolutionary way of looking at this in that you have a key that is actually stored in public. So everyone knows that key. This is a little bit different from symmetric key cryptography, where the whole purpose was to keep your keys private so nobody can intercept your messages and know what you're talking about. So for public key cryptography, there's a couple different algorithms that make public key cryptography possible. I mentioned one earlier, which is EXTA, elliptic curve digital signature, but you don't have to worry about those algorithms. Basically, public key cryptography works like this. Bob provides his public key. He secures his private key. And this is, you could think about this in Web3, right? If you're familiar with the idea of securing your private key, you may have used a wallet, a hardware wallet, where at the end of the day, the wallet's job is secure your private key. Bob signs a message with his private key, and anyone out there in the network or in the world can verify that that message was signed by Bob. So all 3 of these people can see the message, even though they don't know Bob's private key, they know Bob's public key, which allows them to say, this was sent by Bob, right? You can imagine that public key cryptography is really important in the world where we're going to be moving into AI and like a whole bunch of information that could be sent out from anyone. You can imagine it's going to be really important to be able to say, this message was sent by me, so people can verify that it was sent by you and not, created by an AI, even though it looks a lot like you, right? So this is going to be really, really important going forward. And it's also really important for blockchains because this provides the authentication that we need for blockchains. For blockchains in Web3, we have something like an address. So you may have seen down below here, you can see I have 0xF3C. You may have seen something like that for an address. If you've ever gone to Etherscan and seen your transaction on Etherscan, you may see that your transaction is coming from an address. So in the case of Web3, an externally owned account, which is going to be a private key, public key pair, signs a transaction with their private key. Then they broadcast that transaction to the blockchain, and the blockchain nodes are able to recover the public key from the signature and know that this particular transaction was sent from a particular address. So they can look here and say, okay, we all agree that this message was only sent by 0xF3C and not 0xABC, right? Something to point out here, because I will show more examples with hex. Hexadecimal is using base 16. So instead of using 10 characters like we have in decimal, 0 through 9, we can use 16 characters with hexadecimal, which is 0 through F. if you've ever seen an address on an EVM compatible chain, you're going to see that it's usually listed as hexadecimal. When you see that 0x, all that means is, hey, whatever's following this is hexadecimal. So that's why you may see 0x all over the place in Web3 for addresses, for transaction hashes, for things of that nature. It just means this is going to be hexadecimal. It's not actually part of the data itself. But those are addresses down there, and we can verify that an EOA 0xF3C, in this case, sent this transaction. So if you're a nerd like me, you may want to know how the public key relates to an address. So I talked about this idea of a private key, public key pair. An EOA is a private key, public key pair, but we really care about in Web3 our address. You could think of the public key as an address, but there is a short algorithm to go from a public key to an address that all blockchain nodes do in order to derive your address. So if you put out your public key, they can get your address by taking your public key, hashing it. This produces a 32-byte output, and then the last 20 bytes are used for the address. So if you've seen an Etherscan address like this one down below, this is a good example of an address that's been derived from a public key, which is going to be something that is mathematically linked to the private key in such a way that you can sign something with a private key and verify it with a public key. Cool. So what are our key takeaways? Key takeaways are that transactions are secured by public key cryptography or asymmetric key cryptography, right? You can think of it either way, but now that you know that public key cryptography is the using of two keys, you can also understand when someone says asymmetric key, right? It just means there's a different key on both sides of the communication. Transactions are signed by EOAs, which produce a signature, and that allows any blockchain node or anyone looking at this data in the future to say that that person was the person who signed this transaction. The signature provides nodes with the ability to authenticate that sender, which then allows them to do some state change on your behalf. So if you've ever interacted with the blockchain, you've probably signed a transaction, sent it to a blockchain node. That blockchain node then derives your address from the signature and says, okay, this came from this person's address, right? Great. So let's jump into transactions next. So we talked about externally owned accounts. Externally owned accounts are the things that always sign a transaction, and they sign a transaction using public key cryptography. Now I want to talk about what's inside of a transaction. So what's inside of a transaction? Let's score your transactions knowledge. Did you know that transactions can send value from one EOA directly to another? Did you know that transactions can deploy smart contracts or communicate with a smart contract? Did you know that every transaction is unique? We'll talk about why that is. And did you know that transactions execute one at a time on EVM compatible blockchains, at least as it stands today? What this means is transactions execute one at a time. They're not executing at the same time. So when it comes to the EVM, when you execute a transaction, if you are programming a smart contract function, you can know that that transaction has the entire EVM to itself at the time that the transaction is occurring. So no two transactions are occurring at the same time. So you don't have to worry about what if a transaction is also accessing this function at the same time and worry about state changes between when your transaction started and when your transaction finished. So what's in a transaction? Transactions have a few different parameters that we're going to be talking about, most important of which are value, gas parameters, and code. So let's take a look at those. So in a transaction, when you are a EOA, when you're a user, you might put a few properties in a transaction. You might put some value when you want to send some ether or whatever the native currency is of the blockchain to another EOA. You might program in a to address when you're talking to a contract or another EOA. You will program in some gas parameters, which basically tell the blockchain, hey, this is the max amount of gas that I'm willing to spend. We'll talk about what gas is in just a moment, and how much I'm willing to spend per unit of gas in the native currency of that blockchain. You might also send some call data. So if you've ever heard the term call data, blockchain is interesting where if you work in the space, if you're in the space as a user, very often these technical details like call data find their way to the top level, to the surface level, where we hear these things all the time. If you've ever heard call data, it's referring to this data that's on a transaction or a message call between contracts that is targeting a function on the smart contract and sending some parameters. So we'll take a look at an example of that. And then a nonce is what makes every transaction unique. This is really important as like a sort of tangent here on digital signatures. We talked about digital signatures being really important in that you can derive the who sent that transaction. It's important that these transactions can't be replayed, right? If you wanted to be able to send a transaction twice, but you didn't want that transaction to be, replayed 15, 16 times, you need to make every transaction unique. So there's something called a nonce, which will make the transaction unique so that the blockchain can say, hey, this person only wanted this transaction to execute once and not multiple times. So a quick word on gas. I know this is a little bit technical here, but it is important to differentiate what gas is versus the native currency. So I think it's often misunderstood that gas is the same thing as ether, right? So when we talk about gas, we do pay for gas using ether or whatever the native currency of the EVM compatible chain is. However, gas is its own unit. It's actually something that directly corresponds to the low level, what are called opcodes inside of the EVM blockchain itself. So the EVM has these opcodes where you can actually do some of these low level operations like adding two things together. And when you talk about these low level opcodes that are just, most of the time, smart contract developers don't even program at this level. They program at a higher level in Solidity, but those your program gets compiled down to actually target these opcodes. These opcodes have a specific amount of gas associated to each one of them. So at the end of the day, if you run the same opcodes, you are going to end up with the same amount of gas costs. So that's important to sort of differentiate this idea between ether and gas. Gas is always going to be consistent using the same opcodes versus ether, which is going to be how much you pay for unit of gas, which depends upon the market at the time. So if the blockchain is doing a lot of execution, if there's a lot of throughput through the blockchain, you're going to pay more per unit of gas because everyone's trying to get their transaction in at that time. However, you may be paying for the same amount of gas because you're trying to execute the same amount of opcodes or the same opcodes as you would even in a time where there's less transactions going on. Okay, so the different types of transactions that you might see, one is deploying a contract. So for deploying a contract, what you do is, as a smart contract developer, is you take a contract in Solidity or a higher level language, and you put it through a Solidity compiler or whatever the compiler is for the language that you're using. This is actually going to break it down into something called bytecode, which you put into a transaction. And again, this is something that an EOA signs and sends to a blockchain. And what comes out of that is a contract at the end of the day that then lives on the blockchain. It has its own account. It has its own state where the code lives. It has an address, it has a balance, and it also has this thing called storage, which is where it can store all of its state variables. So if you've interacted with something like Uniswap, where you are exchanging one ERC20 token for another, that the Uniswap smart contracts, they would have some sort of storage in there that would say who has what balance inside of the Uniswap pools and how much does it cost to exchange one ERC20 token for another. So you could also have a transaction, like I mentioned before, between an EOA and an EOA. This is going to be the simplest way to transact when you're just trying to send some value from an EOA to another EOA. In this case, you wouldn't really encode call data. You could if you were going to send a message. You may have seen before that people have sent messages to each other on the blockchain. You could encode a message for no other purpose than to have that stored on the blockchain. But when you send value from one EOA to another, the important parameter here is the value. It's going to be the Ether or the Matic. If you're on Polygon or whatever EVM compatible chain you're on, you're going to be sending the value here. The gas that it costs to send a transaction between an EOA to an EOA is always going to be the same. It's going to be a static number that it costs to send a transaction because you're not interacting with a smart contract. And then finally, the last type of transaction that you would see is a transaction that's communicating with a smart contract. This is where we're going to see call data come in. So if you've heard this term call data, what happens is when you are trying to communicate with a smart contract from an EOA, you sign a transaction that has some value in it. It might be Ether. You have some data in there. That's going to be the call data. And that call data is going to target an entry point on the contract, right? So I did highlight here the 5B. 5B is actually an entry point into a contract at the lowest level where you can actually say, I want to start executing opcodes from that point using this parameter that's been encoded within the call data. I make this point of it being bytecode just for the purposes of being complete here. Although for the most part, as a Web3 developer, you're thinking about things in Solidity. So it's a little bit easier as a developer to think about these things versus taking a look at something like what's shown here, which is the opcode level, the low level. And then other contracts can communicate with each other via something called a message call. And a message call allows a contract to communicate with another contract, encoding call data between these contracts as well to target other entry points into other smart contracts. These message calls can also include value. They can send Ether from one smart contract to another, and they can also include a gas parameter to say, this is the max amount of gas that you're allowed to spend out of this transaction. Now, everything you see here on this slide is one transaction. So in one transaction, and you've probably seen this if you've interacted with a blockchain before and you've taken a look at something like Etherscan, in one transaction, you could send some call data to a smart contract, and that smart contract can call many other smart contracts. And then at the end of the day, it's going to walk all the way back up to the original contract where the transaction is going to conclude. All of that is one transaction. And like I said before, transactions all have the EVM to themselves. They happen sequentially, so they only occur one at a time. So when you make your transaction, it can call many contracts, which could change state, storage across all of these contracts, come all the way back up the call stack to you, concluding your transaction before somebody else's transaction happens. So you could interact with Uniswap, and Uniswap could exchange one ERC20 for another ERC20, which are separate smart contracts, change the balances in both of those smart contracts, and then come all the way back up to the original Uniswap contract before somebody else gets to execute on the EVM. So what about when things go wrong? You may have heard this idea of a transaction failure or a transaction revert. So when somebody transacts and something goes wrong, let's say they don't have permission to do whatever they did, you could do a transaction into contract A, and contract A could call into contract B, and contract B could say, no, this is not okay. And contract B, whatever state changes happen in contract B, if it calls a revert, it will actually revert those state changes, and those state changes won't occur. Contract A at that point does have the ability to say, I still want my state changes to occur if it doesn't want to revert from there. However, if contract A does revert, like it does in this case, where it's saying, I want to require that the message call is successful, then what you have at the end of the day is something called a transaction failure. A transaction failure and all reverts all cost gas because they did occur. They did happen on the blockchain. So you are still asking the network to spend their resources. So at the end of the day, as a user, you do have to pay for that gas. The EOA has to pay for the gas because that transaction was included in a block. And now somebody has to pay for that transaction being there. So you may have heard me just say the term or the idea that a transaction was included in a block. So we haven't really talked about a blockchain on a high level, but now you may understand that a blockchain, when you're thinking about it just in terms of blocks, is really just a collection of blocks. It's a bunch of blocks that each have a bunch of transactions in them, right? So if you take a look at this on the left-hand side, you see that we have 3 blocks, each of which have 3 transactions inside of them. And each of those transactions is going to make some state change on the blockchain. And the blockchain is going to agree upon some state, which now, if we're thinking about this from the low level, from the Web3 developer's perspective, we know is a bunch of accounts. Those accounts, like an externally owned account, has an address and a balance. Or if it's a smart contract, it may have code and storage to be able to store changes, to store variables, things like how many ERC20 tokens are stored in this Uniswap pool is something that Uniswap is going to have to keep track of inside of its storage, inside of that smart contract. Great. So what are our transaction takeaways? Transaction takeaways are that transactions communicate value, which could be the native currency of the blockchain, which is the native currency of the blockchain. It would either be Ether in Ethereum's case or Matic in Polygon's case. Whatever EVM compatible chain you have may have its own native currency. It's going to be data, which is the call data, right? Which is going to target some function on a smart contract. It's going to target an entry point where it could start executing code on the smart contract, as long as the smart contract was programmed in such a way that that entry point is allowed. And then gas preferences saying, hey, what am I willing to spend per unit of gas? And how much gas am I willing to spend in this transaction? That way you can only run up a certain high level of a bill, right? You can only spend X amount as a user. You cannot spend more than you put into your transaction. Transactions execute on chain and they make state changes. So these state changes are going to be everything that we care about inside of a blockchain, right? If you've interacted with a protocol like an Aave or Uniswap, you've made state changes. If you've sent value from one EOA to another, you've made state changes, right? You've changed the value that's stored in the different accounts. A transaction always begins at an EOA. So when we talk about things like account abstraction, it's important to remember that a transaction has to begin at an EOA somewhere. Even though the account may be abstracted from the user, some EOA somewhere is signing that transaction, right? And a transaction can involve many message calls into many smart contracts, eventually coming all the way back up the call stack to either revert and fail the transaction or succeed and make some state changes. Okay, so back to the big picture. So now that we've been through a lot of this on a lower level, maybe some of this is starting to look a little bit more familiar on the bottom half of the slide. I hope it's starting to make a little bit more sense. And so some of these things are a little bit more demystified. And that way, the next time you take a look at Etherscan, it's a little bit more clear what's going on behind the scenes, right? Which I think maybe it's just an artifact of the blockchain and Web3 as it stands today, or maybe it's something that we're always going to get used to as Web3 users. You do find yourself often seeing these low-level details, right, as a user, taking a look at the blockchain, taking a look at Etherscan. So hopefully these things are starting to feel a little bit more familiar, where when you are an EOA, you send a transaction that interacts with contracts, and those contracts can call other contracts and change blockchain state. And blockchain state at the end of the day will involve a little bit more than what I have there on the bottom right, but you can think of as a bunch of accounts that either have code and storage if they're a blockchain, or a balance and nonce, or sorry, code and storage if they're a smart contract, or a balance and nonce if they're a smart contract or an EOA. These are your different accounts on an EVM blockchain. Okay, so at this point, you may be wondering, what about queries? So we talked about transactions, which are state-changing things, state-changing messages. When you want to change something about the blockchain, you send a transaction saying, I want to change something, and that is going to cost you a certain amount of gas to be able to make that change. It's going to live inside of a block, and that block is going to get executed, and it's going to cost somebody some gas for all those different transactions. But what about queries? What about when we want to read data from the blockchain? How does that work? So test your knowledge on queries, on reading. Did you know that queries do not cost gas? That queries do not execute on the network. There's no state changes for a query. When you're reading blockchain data, you're not executing something on the network. You may be executing something on a single blockchain node, but you're not executing on the network. It's not going to go inside of a block and change make a state change. With ETH call, which is a specific method that we can use on the core node API, we can execute a message call on a blockchain to retrieve data. And with ETH get storage at, we can look up storage variables on a contract. This is actually a really interesting note that surprises people coming to the blockchain for the first time. Even developers who are really familiar with programming come over to the EVM chains and are surprised by this. When you have a smart contract and you store a variable on that smart contract, it's public for anyone to see, because at the end of the day, that database is transparent. Anyone could go look it up on a blockchain node. So we actually have a method for this on the core API called eth_get_storage_at, where you can say, hey, this contract right here, Uniswap, I want to know what's stored at this very specific storage location. And if you know how to find that storage location to pull the data out, you can just go and grab that data directly without interacting with a method. You can go straight to the database and understand what that value is. Okay, so some of the standard APIs, this is going to be part of the core node API, which is core product to Alchemy. We provide this ability to be able to look up these different methods, some of which are for transactions. Sending raw transaction data is going to be something where you want to send a transaction to the blockchain, but there's also read-only methods, which are going to be more specific to what we're talking about here, which are queries. So let's take a look at a few of those simplified. So we have ethcall, which I talked about a second ago, where you send an unsigned transaction. So now that we talked about digital signatures, you can understand what a signed transaction is. That's when an EOA signs a transaction and says, I want to pay for the gas for this transaction to make some state changes on the blockchain. An unsigned transaction is when nobody signs it, but you're sending it to a blockchain node to simulate the transaction to get some value back, or to understand what's happening when the transaction goes into the blockchain. You can also use things like eth_get_balance if you want to know what the balance is at a particular address. So this could be used for an EOA or smart contract. Smart contracts can also have a balance. You can get transaction count, which is actually going to give you what we referred to earlier as the nonce. That thing that makes every transaction unique is going to be the number of transactions that they've sent. It's just a count, which is going to make it so every time you sign the transaction, it's going to produce a different signature. There's also methods like eth_get_block_by_number or eth_get_block_by_hash, which is going to allow you to look up blocks on the blockchain, or eth_get_transaction_receipt, which we'll talk about a little bit in a moment, which is going to be really useful for things like logs. Or from the Solidity side, you may have seen it referred to as an event. And I'll talk about why these things are super, super important. So some of the other APIs that we provide at Alchemy are all these enhanced query APIs, all these additional tools that we allow developers to use, which are going to solve some of these developer pain points that I talked about earlier, which makes it really difficult to build scalable Web3 applications. Fortunately, a lot of these developer pain points have been identified, and now these tools are making it really easy for developers to be able to solve these problems. So let's talk about events. So for events, this is something that I kind of alluded to just a moment ago with transaction receipts. Events are something that happen on the blockchain when you want to categorize some information for later consumption. So let's say we're talking about NFTs, right? For NFTs, you may have heard of the Bored Ape Yacht Club, which is one of the more popular NFT contracts. For the Bored Ape Yacht Club, if you wanted to transfer an NFT, you are going to send a transaction where the data, see the data over here, we talked about call data, you're going to encode some parameters and the function to say, I want to transfer this particular NFT. And because it's an NFT, a non-fungible token, you know that it has some unique characteristics, a unique identity, unique ID, where you're going to say, I want to transfer this particular NFT. So you encode this transaction with all the transaction properties. It hits the Bored Apes contract, and what it's going to do is it's going to emit a transfer event. That transfer event is important because if UIs or servers or any other Web3 application wants to be able to listen to when a transaction has occurred, it's going to be important to be able to store this data as a happenstance, as a log, as something that has occurred, so we can sort of look that up later, so we can filter on it. So we could say something like down below, you could see I have here, show me all the transfer events that have happened from the address 0xabc in the last 100 blocks. This sort of filter that I described here is actually something that's part of the core node API. However, there's some developer pain points with NFTs and all other abstractions that we talk about on the blockchain, Like, for example, finding all the NFTs that an address owns. This is actually really difficult. So if you take a look at that developer pain point that I'm referring to down there, finding all the NFTs that an address owns, and you take a look at this image that we have here, it's actually really difficult to sort of figure out how would I find for a particular EOA all the NFTs that they own, right? There's no method on the NFT smart contract that says, here are all the NFTs that that particular address owns, because we have some of those constraints that I talked about with smart contracts that make it very difficult to be able to add new data like that. Smart contract developers are trained to store as little data on the blockchain as they possibly can to make the application work. They're not going to store information like, here's an array or a collection of all the NFTs an EOA owns, because maintaining that collection would be extremely expensive. So instead, what happens is we need to have servers. We need to have computers that are actually designated to store these collections off-chain. This is a developer pain point because you have to go and do something like listen into all the transaction receipts and say, let me look up every single log that has occurred where there's a transfer. And every time there's a transfer from this particular address to the address that I care about, I'm going to log that maybe in a database, and I'm going to keep track of that collection of all the NFTs that they own. Fortunately, for developers, there's a NFT suite that Alchemy provides that allows you to, within one method call, look up all the NFTs that a particular address owns by just saying, give me all of the NFTs that this address owns. This is a developer pain point that is surfaced because we're talking about something that is an abstraction on top of the blockchain, an NFT, which is not something that's part of the core API. A bonus, you could use webhooks here, which allow you to actually get notified of this event when this event occurs, so that you can actually do something based upon that event immediately if you needed to. Okay, so one last thing that I want to dive into here, which is going to give us a little bit of an elucidation on what I just talked about, is the ERC20 token standard. I mentioned this idea of having abstractions on top of a blockchain. When we talk about token standards, or when we talk about any standard that is a smart contract standard, this is something that lives on top of the core API, right? Smart contract standards are something that smart contract developers have agreed upon is a common way to interact with some sort of an abstraction. So in this case, when we talk about the ERC20 token standard, we're talking about a template that allows you to interact with the different ERC20 tokens on a blockchain. And this is important because this gives us the ability to build protocols and build tools and build APIs that can communicate with these ERC20s in a predictable way. So test your token knowledge. Did you know that ERC20 tokens are not native to the EVM? If you didn't know that, I probably just spoiled it for you just a second ago. They're not native to the EVM. ERC20 tokens are something that are built on top of the EVM. They're a smart contract standard that allows us to create smart contracts that adhere to the rules set forth by the ERC20 standard. Each token keeps track of its own set of balances. So this is something that's pretty surprising, I think, to Web3 developers coming to the space. This is definitely something that's surprising to users and explains a lot of the reasons why there's frustrations as users oftentimes when it comes to web apps and keeping track of their tokens. Each token keeps track of its own set of balances. So when you look at your wallet, maybe you're looking at MetaMask, maybe you're looking at a hardware wallet, maybe you're looking at Etherscan and you're looking at your particular address. What's often you see is that you take a look at your address and you see a bunch of tokens listed. That's not something that is native to the blockchain to be able to go look at your tokens. That's something that has to be done additionally off-chain to figure out where all of your tokens are, because every token is its own contract that stores its own set of balances inside of that storage that I was talking about earlier. So there's no way to stop somebody in the standard from sending you tokens because a token is its own separate smart contract where they can store a balance to keep track of how much you own of a particular token. So when somebody sends you some tokens, some ERC20 tokens, they're really modifying storage of an alien smart contract, a smart contract that may have never interacted with you before. It doesn't have to interact with your account in a direct way. It just keeps a record of your address and then modifies your balance according to that contract in its storage. So fortunately for NFTs, Alchemy does provide a spam filter, which allows you to spam, as a developer, be able to tell which NFT contracts are spam, because there's no way to necessarily stop an account from receiving an NFT. I say receiving sort of like in air quotes, because really all you're doing is changing a storage variable inside of the NFT contract. Now, a really interesting addendum to this is with account abstraction, what you can actually build in into the standard is a way where you can create something that's often called a safe transfer, where in the token standard, you can actually encode something that says, I want to reach out to whoever's receiving this token and ask them if it's okay to receive this token. That's really important, because if you've ever seen sometimes like protocols like Uniswap or Aave, oftentimes when you look at these protocols on chain, the smart contracts own a bunch of tokens by accident, where people accidentally sent their NFTs or their ERC20s to these smart contracts. But if you have something that says, I want to reach out to that smart contract and ask if it's okay to send this token, and the smart contract responds with a revert saying, no, it's not okay, that actually stops somebody from accidentally destroying their tokens, right? Which is pretty cool. You could also program that into a smart contract wallet, which is why I mentioned account abstraction a moment ago as well. Lastly, token standards define how you can call the contract, not necessarily what the contract does. So you may have seen that there are malicious tokens out there, because at the end of the day, an ERC20 token is a set of methods and how you can interact with those methods, but not necessarily what the contract does. At the end of the day, if a ERC20 contract wants to be malicious and program something into the ERC20 token that interacts with your account in such a way that is not good, they can do that, right? So ideally, you don't interact with smart contracts that you don't know what they do, or you don't have the trust that they're doing something that you would like them to do. So this is the ERC20 standard interface. I point this out not because I think that you will necessarily be interacting with these things at the low level, but I just want to point out this is what a standard interface looks like, right? We define as smart contract developers a set of methods and a set of storage variables that say, this is, if you want to be an ERC20 token, like any of the icons you see around this slide, you have to implement these things, right? Here are some required functions that you must implement. So if Uniswap, for example, wants to be able to trade your ERC20 for another ERC20, it knows that as an ERC20, you've implemented something called transfer. And so Uniswap doesn't even have to know about your smart contract. It can know, even though you just created your smart contract yesterday, that your smart contract adheres to the ERC20 standard, which means there's a method called transfer with predictable arguments that you're going to be sending to that method. These interfaces are super important because they allow us to build protocols like Uniswap or APIs like the token API that allows us to solve developer pain points, like things like how many tokens does one developer own? I talked about a moment ago, that's not something that's native to the EVM. That's something that has to be done off chain, right? That's a difficult thing to do. But fortunately, because we know that there's a standard interface, we can actually be able to do this across all the ERC20 tokens and provide this for developers so they can build awesome Web3 applications. So real quick, I just want to take a look at maybe how we picture what happens inside of the blockchain versus how it actually happens more technically. So I kind of alluded to this, but when you look up an account's balance in the top half of this slide, you may be thinking as a user that in your account lives 9 DAI, right? But when we took a look at the accounts earlier, we know that for an EOA, there's only 2 things in there that really matter for an EOA, which is the balance, which is going to be the Ether balance, the native currency balance, and also the nonce, which is going to be a replay protection for transactions. At your account, it doesn't live 9 DAI. Instead, what actually happens is there's a DAI contract that lives on chain where they keep track of your balances. So if we actually want to know what the balance is for a particular user, we have to go to that smart contract. We have to find the DAI contract on chain and ask it, hey, what's the balance for this user? This is why it's not easy to look up the balance for a particular user, because you have to know about every ERC20 contract in existence, right? That's really difficult to do. In order to know about every ERC20 contract in existence, you have to be paying attention to every transaction that ever occurs on the blockchain. And you have to say, is this a deployment? Is this a deployment of a contract? If it's a deployment of the contract, then you have to figure out, is this an ERC20 contract? And that's difficult to do because at the end of the day, what's being deployed to the chain is bytecode, right? So you can look at that bytecode, and depending on the standard interface, you can determine whether that's an ERC20 contract, and then be able to start listening in and say, okay, is this something that users will care about and they want to see in the UI when we reflect their token balances, right? This is why it's important to have these awesome developer APIs like Token API to be able to look up a developer's balance, right? And it's not something that's native to the EVM, so it's not something that's part of the core API and not something that's necessarily easy to do. So a transfer is similar, right? You might be thinking, I want to send some DAI to my friend. And so you say, okay, well, I'm just going to, program in a transaction that sends 2 DAI to Bob, right? And so you might be thinking about it from the top part of this slide. I'm going to take 2 DAI out of my account and put it in Bob's account. But really, more technically, what's happening is an EOA is signing a transaction with some call data, sending that to the DAI contract and saying, hey, I want to transfer to this account from my balance to DAI. And then the smart contract is then going to run some opcodes, right? It's going to run some data, or it's going to run some code that is going to then adjust those balances in storage. And then it's going to emit a transfer event. And we talked about events a moment ago, which are really, really important for UIs and servers to be able to listen to those things and be able to then categorize that stuff and be able to show it to users at the end of the day so we can keep track of all of their balances and know the latest state of the blockchain. So for smart contracts, one last thing I want to point out here is that there is an interesting thing that you may have noticed as a Web3 user, which is that oftentimes when you're interacting with something like Uniswap or Aave or any of these other protocols that use ERC20 tokens, oftentimes you have to sign 2 transactions to do what you want. And that's a really weird thing that happens in Web3. That's an artifact of how ERC20 tokens work, which is you have to do something called an approve and then a transfer. And this is something that's a little bit hard to see, but I'm hoping that these images help you understand why that's important. If you did a transfer to Uniswap, right, you wanted to send some DAI into a Uniswap pool, you could talk to the DAI contract and you could say, hey, DAI contract, I want to send some DAI to Uniswap. And then Uniswap doesn't know that that transaction happened. So how does Uniswap respond to this transfer, right? The image you see in the above portion of this slide doesn't interact with Uniswap in any particular way, right? You are going to the DAI contract, to the contract, the ERC20 contract, and you're saying transfer, but Uniswap is not involved. So it doesn't know to adjust the pool in a way to be able to send you out the ERC20 token that you're looking for. So instead, what actually happens is that when you're trying to send some DAI into a Uniswap pool, we think about it as a user as taking some DAI and just putting it in the Uniswap pool. But more technically, what you have to do is you have to go down below and you have to do a first transaction 1 on the left-hand side, and you have to say, hey, DAI contract, I approve Uniswap to pull some tokens out of my balance. And DAI contract says, okay, and it emits an event in case anyone's listening for approvals and needs to use that for their execution. And then for transaction 2, we're going to then, from the EOA, so it's actually starting from the other side. You can see the key is on the right-hand side. We're going to say, hey, Uniswap, you can now transfer from my account into your account the balance of 2 DAI. And Uniswap can go pull that out of the DAI contract. It can do a message call to the DAI contract, getting that balance, and Uniswap will check that that balance has been added to its pool. Then it will run its execution. So if you ever seen this approved transfer from flow and you've been confused as a Web3 developer or Web3 user why this has to happen, it's an artifact of the token standard, and it's something that is surface to us as Web3 users. I think that's always very interesting about the Web3 space, is that these low-level technical decisions end up getting surfaced to the user at the end of the day, and to all developers as well. Great, so last slide here is ERC20 takeaways. A contract standard is an agreed upon set of methods and definitions for a contract. So you see a bunch of ERC20s on the left-hand side of this slide. Each of these adhere to a certain set of methods that we know that we can call the balance of an Aave token or the balance of a DAI token, and they behave, or at least they respond in the same way. They may not have the same code inside of them. A contract standard doesn't designate what a contract does, it designates how it interacts, how you can call it, and what it's going to respond with. It's not part of the core API because this is a template for smart contracts. It's not something that's baked into Ethereum itself or any EVM compatible chain. It's not at the chain level, it's at the smart contract level. This is why it's important to build smart contract APIs that solve these developer pain points, like tell me how many tokens this particular person owns. Standards provide protocols with a way to interact with new and future contracts that adhere to the standard. So Uniswap could have been deployed 4 or 5 years ago and interacting with ERC20 tokens that were only deployed just yesterday, right? Because it knows that this token is going to behave in this particular way.